Good, welcome. I will start today with a brief review, then show you a very different kind of Markov random field just to give you an impression of the kind of modeling that can be done. And then we'll be talking at length about how to find the most likely solution in an undirected graphical model, or equivalently the minimum energy solution if you prefer to think in terms of energies. Books, well, this one covers much more than you need, but it is a nice book. It does not cover the connection between MRFs and combinatorial optimization, but then in combinatorial optimization itself, this is one of my favorites. Okay, starting with a brief review of what we saw last time. I used this example for motivation, saying that we can imagine training a classifier which will give us a pixel-wise prediction, which we can use as a unary term in our Markov random field. And well, we will expect this classifier to make mistakes because some of these classes look quite similar. And then we want to inject prior knowledge, for example, here which class can be adjacent to which other. This prior knowledge we can code in terms of a prior, which I circled here in green. And we have also been sampling from this prior in the lecture, and this is also what you've been doing in the exercise. The Markov random field itself, the undirected graphical model, looked like in this picture where I've color coded each of the terms. So the purple circles represent the random variables for which we want to estimate the most likely state, the posterior probability, given our prior and given our measurements. The measurements themselves were here shown as shaded random variables to say that they have been observed, so they're fixed at some value. And then we also have the opinion of our unary term, which is encoded in a conditional probability table. So if we did have 20 classes, then we would have for each pixel a vector of length 20 that tells us how likely is it that this observation is associated with such and such class. And then the prior, we have been discussing smoothness priors, is here shown in terms of these green pairwise factors. This MRF is for 4 pixels, so usually you have this 1 million pixels with 1 million nodes. But this is a very typical structure for Markov random field that has been used abundantly in computer vision. And well, examples where this can be used are semantic segmentation in biomedicine, like you see above, or semantic segmentation in automotive applications, as you can see here. So this is one example from the so-called Cityscape dataset. These are results of Daniel Kawecki, who is writing his master's thesis. And you can see color-coded the predictions of, in this case, a neural network for each pixel. And it does quite well in general. Just this vehicle to the left, I'm not sure if it's a bus or a truck, confuses the network a lot. So the network thinks that this is partially tram, partially bus, partially train or something. And if we did have a smoothness prior here, this was not used in this example, then there is a chance that this might lead to a prediction which is more homogeneous for this vehicle. On the other hand, we would not maybe want to use the same smoothness prior for all classes. So if you look at these thin poles, for example, if we also imposed a smoothness prior here on these thin gray poles, there is a chance that we would lose them. But we have there is the possibility to have the smoothness prior act only on certain combinations of classes and not on others. Just means we have more parameters in our procedure, which we need to train. Okay, and yet another example. This is an example where one tries to estimate a depth map from 2 cameras, and such a depth map can either be continuous or discrete. Here we're talking about discrete MRF, so I could pretend that it's just maybe 50 different depth classes that are being used here. And also in such cases, it's quite useful to have a smoothness prior of the type that you've been looking at in your exercise. Okay, so all of these applications could use this very same graphical model defined on a Cartesian lattice. And to show you the modeling freedom that you have, or the riches of Markov random field, I want to show you a different example, one which is less regular. Go ahead, you have a question?
My question is, can we encode the prior into the vector graph as well? In the vector graph, there is only unary term and the pairwise term. How about how to encode the prior?
Yes, the prior is encoded here. Yeah, so the prior in this example, I circled in green. Green? No. Okay, sorry, let me stop and start this. Let's see if I can have green. Okay, this is the prior. Yeah? And the prior has been encoded here in terms of these pairwise factors.
And the figures you showed us is using some techniques to sample the prior, the semantic segmentation.
Well, this here we did sample from the prior, yeah, using these Markov chain Monte Carlo techniques, and in these other figures, so actually here a Markov random field has not been used, but a Markov random field of the type shown on top could be used here. This is what I was trying to say, to improve results, but I'm not showing that it does improve results. I'm just suggesting it, okay? And here, well, this depth map, it is already fairly smooth. So these are not my results. You see the web page from which I have grabbed them. I would claim that some smoothing has already been happening here to get this depth map on the bottom. More questions? Okay. So I promised another very different model. Here I'm using something from our own work. Shown on top are a few patches from a video. In this case, these are videos of larvae, and our cooperation partner, Slatic, she is interested in tracking all of these larvae. And one way on the step to getting a full tracking is to actually figure out how many are in a given clump. And if you look at these images, for example, are 0 larvae. This is one, but it's one which has gotten up on its behind to look up at the camera and look at us. This is why it's so bright. These are actually 2. They're just being really cozy here. This is maybe easier to see. These are 3. There's 1, 2, 3 larvae. These are actually 4. You see 1, 2, 3, 4. These are actually 5. These are actually 6, and these are actually 7. Now, the point is that on some of these images shown here, it is very difficult to estimate, even this basic question, how many larvae are there in these images? However, I was saying that this is video, and these videos have high frame rate compared to the velocity of the larvae, so we can exploit the information of what's going on before and what's going on afterwards to come up with a more informed estimate. So here on the left-hand side are shown 3 patches from 3 subsequent frames. And now what we can try and do is we can segment in each of these, we can make a foreground-background segmentation in each of these frames. And here we will find 2 2 foreground objects, 2 foreground objects, and 1 foreground object. Sorry, I should have used a different color here for consistency. T is time, yes. So 1, okay, good. And now, because they are so close in space, we can, well, build a graph that connects these segmentations, and we can enforce prior knowledge. We have 2 kinds of prior knowledge. One is that in this particular experiment, the larvae, they cannot escape, so they cannot fly away, they cannot burrow into the material in which they're crawling, and there's also no bird coming by to steal one of them. We know that a larva cannot appear or disappear, so we have a conservation law. And we have, on the other hand, well, again, conservation law, which means that if this here was, let's say, if these were A larvae, and this here was a number B, and this was a number C, if there are no other segments in the vicinity, then I have prior knowledge that whatever the number A is, it has to be B plus C. So I'm not saying how many larvae there are in A or B or C, I'm just saying that this equation here must be fulfilled. This is also kind of prior knowledge. And I can now build a conditional probability table, or I can build an energy table. For example, let's say between these detections x2 and x4. So let's say we're looking at this factor here, and we're looking at the energy that I get between the variables 2 and 4. Let's say x2 could be 0 larvae, or 1 larva, or 2, or 3, or 4, or 5. And similarly, x4 could be 0 larvae, or 1, or 2, or 3, or 4, and so on. And now what energies would I give to these different configurations here? So this is the energy depending on x2 and x4.
On the diagonal, the probability should be quite high, and the more you go to the off-diagonal elements, the probability should be smaller. So, for example, a 0-5 combination should have a very low probability.
Okay. Here I've been arguing in terms of energy, so let's talk about energies. Yeah. So you said that on the my energy penalty on the diagonal will be 0. That's correct. And then on the off diagonal, now on the off diagonal it depends. If I believe that with my graph construction, so with this arrow here, that I cannot possibly have made any errors, then, and if I really want to enforce this constraint, then I could simply put an energy of plus, well, not infinity, but let's choose some very large number. We would have some large penalty on the off diagonal. Yeah? And if, for example, at the vicinities of my field of view, if larvae can appear or disappear, then I should be doing, like you said, not just have 2 numbers, 0 and a large number, but then I could have some banded structure that increases as I go away from the diagonal. Exactly. And well, for this was a pairwise factor, and up here we would have a 3rd order factor. So here we would have an energy that depends on the variables 1 and 2 and 3. And then I could again draw a table, except now it would have to be a 3-dimensional table of possible energies. This is my prior knowledge. And then, of course, so this guarantees me consistency. but now I also want to inject the actual observations. So I don't just want to know that A equals B plus C. I want to also know, well, what is A? So how many larvae do I think are in there? And for that, we can again train a classifier. And somehow I cannot change colors. All right. So here we would have, for example, a potential for the first variable here, psi1. And this potential could be a vector of numbers. So how bad do I, or how much do I believe that this is, let's say, 0 larvae? I don't really believe that these are 0 larvae because this is a big foreground object with a lot of bright pixels. Yeah? So I'm going to give this a very large energy. I'm now making up these numbers. Okay, could it be 1 larva? Yeah, maybe. Could it be 2 larvae? That's quite likely. Could it be 3 larvae? Maybe less likely, and so on. Yeah? So this is a vector. If I formulate this as energy, this would be a vector of numbers here. Low penalties, if I think that could be the correct number, and high energies if I think this could be the wrong number. Yeah? So these are my unary terms. And the prior, like the name suggests, that comes from prior knowledge. The blue term here comes from some classifier, maybe from some random forest, which we have been training with a couple of examples. Now we need to give this random forest features, of course, and one possible feature could be to say, how many pixels in size is this foreground object, or what is the average gray value, or whatever you can invent here. And now we have these 2 kinds of factors. We have these likelihood terms, we have these prior terms, and now we're interested in finding the configuration of random variables or the solution which has the greatest posterior probability. Yeah, so we're looking for the lowest energy interpretation of the scene. And hopefully we would get what I've shown on the right here, namely that variable x1 would be set to a value of 2 to give me 2 larvae, and then the rest would all be 1 larva each. Okay, so this I have also shown here in terms of a factor graph. I just wanted to show that factor graphs need not always be as primitive as the one that we've seen last time. So they don't always need to be defined just on a Cartesian lattice. They can live on a more complicated structure. In this case here, the structure itself has been generated from the observations, because I can only construct this graph here once I have watched the video. And we have also seen here that these priors, they cannot just be pairwise terms, they can also be third order or can be higher order factors. Okay, and then by the way, so here we see a specific example. So from left to right here is time. And if we listened only to the unaries, then we would get the color-coded results that you see here. So for example, looking at the unaries, the prediction was that this cluster here would be 3 larvae, and this cluster here would be 2 larvae, and that would also be 1 larva. So I'm just reading off, the colors that are shown here on the right-hand side in the color map. But this is if we only take into account the unaries. And if we now use our prior knowledge, if we use this whole model and then find the maximum posteriori solution, which is also called doing inference, if we do inference, then we find the solution on the bottom. And well, this is of course a cherry-picked example where then, you know, the result before using the Markov random field is wrong, after using the Markov random field is correct. But besides, you know, or beyond the cherry picking, if you just do the statistics and count what was the error rate before or after, then it actually does become better if you use this random field, which was of course the point of the whole exercise. Okay. Any questions? Yeah.
Could you please the below the factor graph, the VPI, which is Leitcode, which is prior?
Yeah. So I've used the same color code. Blue here has been the likelihood, and green has been the prior. Yeah. So here the blue boxes, they represent the estimates that I get from looking at the video to decide each foreground cluster, how many larvae do I think it contains. And the prior encodes the conservation laws. More questions?
Like, is this system analyzing all the different frames as a whole? Like, when maybe the advantage then is that you have like, well, you have some estimation for the first picture, and then you go to the second picture, and then you maybe get a second expectation, maybe based on the first one, but then you find out, well, the first one, I have to update maybe my
Estimate, yeah.
Yeah, my estimate based on the second, like you can go forward and backwards in time. Is this also implemented in this kind of system?
Okay, it's a good question. So the model, as it is written here, extends over all of space and time, yeah? Which is an advantage and a disadvantage. It is an advantage in the sense that this gives you the best possible estimate. It's a disadvantage in the sense that the computation can become quite costly. Yeah? But the model itself is just an energy depending on all these variables, yeah? On x1, x2. In our case, I only showed 5 variables, but if there are more time steps, there are more variables. The energy function depends on all of these, and this energy function itself makes no prescription as to how we want to solve it. You just suggested that we somehow solve it forward in time and then maybe have a backward pass to correct for or to take into account new insights that we've gotten from later on. Yeah? And indeed, what you describe here in words exists as a computational strategy. This is called belief propagation or message passing, where you can start from somewhere in your graph and propagate messages, and you propagate all the way to the other end, and then you need to propagate backwards. And it turns out that if you do this on graphs which are tree-shaped, so which have no loops, this gives you the globally optimal result, and it's very attractive because then you have a dynamic programming strategy which gives you the globally optimum solution of a combinatorial optimization problem. If the graph does have loops, then you can still use the strategy, but then you need to guess some of the messages and then simply iterate this and hope, and actually it will converge to a solution. But the solution it converges to is not necessarily the globally optimal one, or it's in general not the globally optimal one, because this problem that I've shown here, so this problem with loops is in fact an NP-hard problem. However, it can still be solved exactly on pretty large instances. But, you know, this is a very good question, because once you start having millions of frames, so a very long video, just keeping the whole graph in memory at once, you know, becomes too expensive in terms of storage. And then you may need for example, causal strategies. Causal means that I iterate forward in time, but I only take into account past observations and not future ones. So your question touches on some very deep issues in this whole field of inference or these combinatorial optimization problems. More questions, comments? Okay. Good. So we have written down this energy function, but we have not really said how do we optimize over it. And this is what I want to talk about now. Okay. So how to pose a discrete Markov random field inference problem as an integer linear problem. Yeah? So let's assume that we have fully specified our undirected graphical model. And I've repeated the formula here. So we have a prior, we have a likelihood, we have a posterior, and finding the map solution, the maximal posteriori solution, which is also called inference, means that we now want to find the configuration of random variable z that maximizes this probability or that minimizes the corresponding energy. Now I will only show how to do this for a pairwise Markov random field, so where we have second order factors. Doing it for higher order factors is possible in an analogous fashion, either by direct modeling, or you can always transform a higher order Markov random field into a Markov random field involving pairwise factors only. So it's really without loss of generality that I'm now illustrating it for a pairwise Markov random field. And for a pairwise Markov random field, I have here written out what this family of probability distribution of undirected graphical models with only pairwise factors will look like. So the first term here is again the partition function, which we need for normalization. And then we have a product over all the random variables in our factor graph, and each random variable can be associated with a unary factor, and we're multiplying all of these. And then we have pairwise factors which are here, and we are multiplying over all of those. The very general formula we had seen was, let me see, going back in time, not here. Okay, there it was. So I had written that if you look at this boxed formula here, that in such an undirected probabilistic graphical model, the probability of a given configuration is a product over factors, and each factor can depend on a different subset of random variables. So each factor has its own scope. And so this is the general formula, and what we've just seen is just a specialization of this formula when our factors are either unary, depending on a single random variable, or pairwise, depending on two random variables. Okay, so this formula is a specialization of the other one, which we had seen previously. Is everybody fine with that? Okay. Now I can either talk about probability or I can talk about energy. So I can look for the solution which has maximal posterior probability or which has minimal posterior energy. And so here I've taken the negative logarithm and ended up with these terms here. So we have a set V of vertices or of random variables that we're interested in, and a set E of edges between these random variables, or a set of pairwise factors that we are summing over here. And what's so beautiful about finding the maximum a posteriori solution is that we don't care about this partition function here. This is a constant which we simply ignore. Okay, this is in contrast. Has anyone done the last bonus exercise? So from the last exercise sheet, the very last exercise, sampling from the posterior? Okay, good. So there you look at the whole distribution. So in this very high dimensional space Z, you have been sampling from the whole posterior distribution. So let's say this is probability of Z given X, and really Z is extremely high dimensional. I'm just showing it as one dimensional here. You have been taking into account the whole distribution to come up with, for example, a marginal estimate. In maximum a posteriori, we're simply looking for the highest posterior probability solution. So this is the argmax. Excuse me, argmax that we're looking for here. And for this, we don't need the partition function. And estimating this, so we don't need the normalization, and that's a huge simplification in general. Okay, so if we have 1,000,000 random variables, then we now have a function of 1,000,000 random variables that we want to optimize over. This is a discrete combinatorial optimization problem. How do we solve it? The idea is to rewrite it in a form for which we already have tools. So metaphorically speaking, there are prefabricated tools like a hammer, so we need to make it look like a nail. And in our case, the hammer is called an integer linear programming solver, and I've given some names here. So Cplex, Gurobi, or Fico Express are very highly developed, efficient, fast, etc. solvers for integer linear programs. And I've written here what an integer linear program looks like. We have an objective function which is linear in the variables. So we have a multivariate vector mu, we have a cost vector c, and we are trying to find that solution mu which, well, if I talk about maximization, then maybe I shouldn't call this cost, but I should call this reward vector. We want to maximize our reward. And if I didn't have any constraints, well, then I would simply present as optimum solution a vector mu which points in the direction of my reward, but is infinitely long, because I want to get infinitely much reward. But you know, life usually is not that good to us, so there are always some constraints, and the constraints are also linear in mu. So we have here this equation A mu, so A is just a linear operator, a matrix multiplication. A times mu should be no more than some vector B. That's a linear constraint. And this would be a linear program. And if in addition we require that the solution vector mu have integer coefficients, then this is called an integer linear program. Now, integer linear programs are NP hard in general. So if we manage to rewrite, this in the shape of that, on the one hand, we have not won anything at all. We've just reformulated the very same problem. But on the other hand, we have won something because we have this hammer. Yeah? So if it has the right shape, our problem, then we can apply this hammer. And this is what I want to show down here. Before I start, any questions? Okay. So if we look at our energy function, it has pairwise potentials. These pairwise potentials are a function of two random variables. But we want an objective, so we have terms in there that depend on, let's say Zi and Zj. But we want something that is linear in the unknowns. Yeah? So we would want a function that depends only on one variable at a time, not on two variables at a time. So we need to, somehow, put it in the right shape. And this we accomplish by linearizing the problem. So in particular, for these pairwise factors, one possibility is to do as follows. We can define a new variable, in this case called mu ij, and mu ij here is a binary variable which depends on the two labels k and l that the random variables zi and cj can take. And it is a so-called one-hot indicator vector. So, and these here are, what are the functions called? They show if the statement, one if the statement is true and zero otherwise. Thank you, indicator function. This is why they're called capital I. So we have here indicator functions. So this one-hot indicator vector is 1 if variable I is in state k and variable j is in state L, and it is 0 otherwise. And I'm being a bit redundant here with the indices, yeah, because I'm writing the I here and I'm writing the I there. Without ambiguity, I could omit one of the two, and same for the j. I've just kept it here. I've kept this redundancy for didactics, because I wanted the expression to still depend on the original random variables z. Yeah. So in other words, we create on the one hand one-hot indicator vectors for the state that a single variable is in, and we create one-hot indicator vectors that indicate what state a pair of variables is in. And all of these indicator vectors, we collect them in our huge vector mu. Yeah, so this integer linear program was defined in terms of a vector mu. And here I've written down explicitly what this mu could look like. So this part here would be the one hot indicator vector for the state of variable 1. And then we have the same thing for the state of variable n. And so if we have, let's say, if we have 1,000,000 pixels and we have 20 possible labels, then this part of the indicator vector alone will already have 20 million entries. Okay, so for each variable, one entry for each of the possible states that this variable could be in. And now it gets worse because now we also need indicator vectors for the state that pairs of variables are in. Yeah, so this guy here says if it is 1 only if variable 1 is in state 1 and variable 2 is also in state 1. This one is on only if variable 1 is in state 1 and variable 2 is in state 2. And so on. Yeah, so we have, in this example, with 20 classes and 1,000,000 random variables, these are the ones that code for the state of single variables. And this is the number of entries that I have that code for the state of pairs of random variables. And in this case, I've assumed that we work on a Cartesian lattice, so each pixel has two factors associated with it, the factor or the pixel to the right and the pixel at the bottom. And if I take into account for each pixel, the pixel to the right and the pixel to the bottom, then I get the complete, then I get my Cartesian lattice out, okay? So this is where I get the factor 2 from, because I have one neighbor to the right and one neighbor to the bottom. The factor 20 times 20 comes because the one pixel could be 1 out of 20 classes and the next pixel could be 1 out of 20 classes. And 10 to the 6 comes simply because I claim that I have 1,000,000 pixels in my image. Okay, so in other words, so all these many variables are needed to code for a single labeling of my image. Everybody fine with that? Okay. Now, I can rewrite my same old energy that I had further up. Let's scroll back up. Here, I had talked about an energy of Z, which was a sum of the unary terms and of the pairwise, so unary potentials and pairwise potentials. And now I'm going to rewrite the same energy still as a function of Z, but I'm now expressing it through these mu's. Here we go. It's the same energy depending on the same variable Z, except now I'm using these indicator variables. So for the unary terms, I have a sum over the vertices, I have a sum over the possible labels, and then I have this indicator vector to tell me if variable I is indeed in state K, and if so, it's 1, otherwise it's 0. And then I'm multiplying this with the potential, with the cost of variable I being in state K. And similarly for the pairwise, I now have in the next line here a double summation over all vertices I, all vertices J, the label K that vertex I could be in, the label L that vertex J could be in. And now I have these more complicated indicator variables that are 1 only if I and J are in state K and L. And this is multiplied with the potential, with the cost of I being in K and J being in state L. Okay, and now comes, excuse me for the jumping here, and now comes a crucial step, namely, so far we had an energy which was a function of Z, and the minimization was over Z. And now we just drop the Z's and directly do the minimization in terms of the mu's. Okay, now I get this objective function here, but I will now need to take into account some consistency constraints. And for example, let's say that if I did not introduce these constraints, and if I have a non-zero cost for every label at every pixel, what would the optimum solution look like? So let's say, yeah, go ahead.
Without any constraints, I could just set all the mu's to 0.
Yes. So if all my potentials are non-negative, then the optimum solution here would be to set all the mu's to 0. But that means I get out no labeling at all, yeah, because I wanted my mu to be a one hot indicator vector. So I want one of the labels to be chosen actually. Yeah? And to prevent this kind of trivial solution, which is not a solution at all, I need a few constraints that we will look at after the break.